Oh, hello. Welcome to lecture 20 of Math 2R03. In today's lecture, we're going to be looking at generalized eigenvectors. Okay, we'll be starting a new chapter. And just to kind of give you a recap of where we left off last time and try to kind of give you a motivation for chapter 8, I just want to kind of recall the example that we left off of last time. So we were looking at, say, a linear map from app squared to app squared, and it could be either the real numbers or complex numbers. And it's the linear map given by taking the pair x, y, and mapping it to y, 0. So the second coordinate becomes the first coordinate, and then the second coordinate becomes 0. And we showed that there's actually not possible to find any basis such that the matrix associated to this linear map is diagonal. However, if we use the standard basis, we can get something that looks pretty close to diagonal. We don't get exactly diagonal, but we get this matrix right here in 0, 1, 0, 0. And so we get something that is upper triangular, but not diagonal. Now, the reason we jumped to chapter 8 is because at chapter 5, this is kind of where we left the story. But in chapter 8, they look at the question is, well, how much further can you push this, right? And we're really going to focus on the case of the complex numbers. And although you can't always find a basis such that the matrix is diagonal, you can get close. And so that's kind of what our goal is in chapter 8, is to see how close could we get to being diagonal. Now, it's good to kind of show you what the answer is so you can keep track of how far we are getting towards this answer. So i.e., if you're talking about the complex numbers, you can actually find a basis so that the matrix associated to the linear map is almost diagonal. In fact, you'll end up with something that looks like this. You'll have the eigenvalues down the diagonal. That's always true. You'll have zeros over here. And on what's called the upper diagonal, oops, get back here. On the diagonal just above, we will allow some numbers to be non-zero. And then everything over here is also 0. So what we're doing is we're kind of allowing the diagonal to be non-zero and then the things just above the diagonal. So the subdiagonal allowed non-zero values. So I want you to keep this kind of matrix at the back of your mind when you're doing this. And notice that this matrix here at the top, right here, really has this form because here's the diagonal and we're allowing things on the diagonal just above the main diagonal. And so this is called a subdiagonal. So that's what our goal is, to show that even though it fails to find the property that a basis such that the matrix is diagonal, we can get close. So it's a diagonal matrix with one, maybe other, allowing some other entries along this diagonal to be non-zero. So that's the goal of chapter 8. And I thought it made more sense to jump from chapter 5 to chapter 8 so we can continue this discussion and you can keep some of the ideas that we've been talking about in chapter 5 fresh as we tackle chapter 8. So let me make myself disappear here and kind of introduce some of the things that we're going to study today that we're going to be using as tools to go forward. So assume here now V is just any finite dimensional vector space. And in the first part of today's lecture, we're going to study the properties of the null space of t to the k, where t is any linear operator. So t to the k, remember, means that you're applying the operator k times, one after each other. And we're going to prove a bunch of lemmas about this operator. So the first lemma is that regardless of which linear operator you take, you're getting kind of a chain of subspaces. You have the zero space contained in the null space of t, and that's contained in the null space of t squared, and that's contained in the null space of t cubed, and so on. So you have this kind of ascending chain of subspaces. And the proof is pretty straightforward. Suppose that you took a vector that's in the null space of t to the k. So by definition, that means that t to the k evaluated at v gives you 0. But then if we're interested in looking at what happens when we plug v into t to the k plus 1, right, we have t k plus 1 evaluated at v using the properties of composition of maps. This is the same thing as first evaluating v at t to the k and then evaluating at t. T to the k v is 0, so this is t evaluated at 0, and any linear map sends 0 to 0. So what we have is that v would also be in the null space of the operator raised to the power, operator t raised to the power of k plus 1. Okay, so that finishes our first lemma. Okay, so we have this kind of ascending chain of subspaces. And the second lemma that we need is that we have this ascending chain, and what it says that if some part, when you go from the k step to the k plus 1 step and you suddenly get equality, you get equality along this chain, then it stays equal from then on, right? So if the null space of t to the k is the same thing as the null space at t to the k plus 1, then the null space of t to the k is equal to null t to the l for any l bigger than k. Okay, and so let's give a proof of this. So this fact here just follows from the previous lemma, because the null space of t to the k plus n is always contained in the null space of the next power of t. So really we just need to show the reverse inclusion, that if you're in here, you're in this side for all n bigger than or equal to 1. Okay, so that's our goal. And let's kind of finish the proof. So let v be any vector in the null space of the operator raised to the power t, any vector in the null space of t raised to the power of k plus n plus 1. Okay, and let's think about what this means. So 0 is equal to t raised to the power of k plus n plus 1 evaluated at v. And we can rearrange this so it's t, the operator raised to the power of k plus 1. Oh, I should want to, excuse me, yeah, t to the n v, right? So what we have is that when I plug t to the n v into the operator t to the k plus 1, I get 0, right? So this means that t to the n v is in the null space of t to the k plus 1, right? And by hypothesis, this is equal to the null space of t to the k. Okay, so that's important to know. This is where we're using our hypothesis. So let's think about what this means. We have that t to the n v is in this null space. So we'll go to a new page. So t raised to the power of k of t to the n v is equal to 0. But this means that t raised to the power of k plus n evaluated at v is 0. Right? So this implies that v is also in the null space of t raised to the power of k plus n. And that's what we needed to show to complete the lemma. So we'll pause here and we'll look at some more properties of the null space when we look at a fixed operator raised to the power.